All right, guys, hello. Turn your cameras on if you can. I, again, do not see too many people today. That's too bad. Nobody has been asking me about the exams. That's very sweet of you. I have not yet started grading your exams. I just only now downloaded them and looked at your files. Most of you submitted the files correctly, but with, I think, a few exceptions. So aside from that, do you have any questions before I start? That's very nice. The probability that you will receive them graded, very high. The question is when, you know? It's a Poisson process. The longer the time, the more likely you will receive them graded. All right, guys. So let's go back to the topic that we covered. So we began investigating when is variance of a sum the sum of variances. And I hope you really understand the fact that the expected value of the sum is always the sum of the expected values. There are no exceptions. Yes, and you can actually see what's happening. Right, so always think very simply. What is expected value? It's just summing up an average on a very big table. And when you condense the table to make it look nicer, you get score multiplied by probability. Yes, that's really all that expected value is. And then we defined covariance. Right, covariance is the kavarne means insidiousness. And that where you have to be very careful. The expected value of x minus mx times y minus my, that's just a generalization of variance, where it would be x with x, right? So here we just combine x minus its average and y minus its average. In the case where you use the same variable, covariance is identical to variance, right? So, and then we arrived at this expression. It's very easy to calculate. Just multiply everything on the inside, and then you see that when you simplify, covariance is the expected value of x multiplied by y minus the product of expected values. Good. Now, this number is equal to 0 whenever the first term is the same as the expected value of x times the expected value of y. Do you agree? So for this to equal to 0, that must be the case. And there's no other way. You can see you set it equal to 0, you move expected value x, expected value y on the right, and you see that that's what must happen. And this is equivalent to independence. Correct? You saw how we figured it out. It's really, once you calculate covariance, you realize that this term is just the multiplication. Let me just show it. The multiplication of every x score with every y score, right? And sometimes this probability is 0. When the probability is 0, that means that every realizable x score might not match against every realizable y score. But when this probability splits, that means that this probability is never 0. That means that every x score matches against every y score. That's a necessary condition, not sufficient, guys, necessary. You understand? So, and then when you, of course, have the situation, then you can just factor. You can just group xi with the probability and yj with the probability, and you can see it's just factoring a sum out. This you just have to realize how foiled, you call it foiling, correct? When you have two parentheses, you multiply things out. It's every term from first parenthesis multiplied by every term from second parenthesis. That's how they will combine. So you can then recognize that this can be split apart. Yes, we will see the same parallel with integration. Right? We will not talk about integration just now. We will do that once it becomes important. Yes. And notice that when that happens, that means when x and y are independent, then covariance of x plus then covariance of x plus y No, so covariance x with y is equal to 0, and variance of x plus y is the variance of x plus variance y. You agree? You see what we have here, because we can simplify. What's variance of x plus y? It's covariance x plus y with x plus y, which when you simplify it, when you kind of move things apart and regroup, it's variance x, variance y plus 2 covariance xy, and the same thing with 3 of them. It's just variance x, variance y, variance z plus 2 multiplied by every combination xy, xz, yz. Yes, so that's going to be very important, guys. We are going to calculate variance and expectation of many random variables, not all of them independent. So covariance will play a role in that calculation. Make sure that you take a good note of it. If they are independent, we have that variance of x1 plus all the way to xn is just the variance of the sum. That's the variance of the sum is the sum of the variance, so to speak. Yes. Now let's try to calculate this example, guys. You can do it fast or slow, but that's up to you. We have 5 fair coins. So the triangle inequality, well, I mean, you have to be careful what you mean by triangle inequality. You mean that this is less than or equal. You see, with variance, you can see that those terms might be positive, they might be negative, right? Those terms might be positive, might be negative. So that's why you don't right away think that there is a triangle inequality. This is not generally less than or equal. Right, it's not generally less than or equal, right? So you don't think it's just a variance of x, variance plus y is less than or equal variance x, variance y, because those terms might be negative. Covariance can be a negative number, so it's a bit more complicated comparison, right? What we know from this calculation is just that that's a good, interesting question. What we know from this calculation is that whenever covariance is 0, we have equality here. So then what we have 5 fair coins, and one of the coin is picked at random and tossed, right? So x is the fair coin that was picked. It's either 1 or 2 or 3 or 5, you understand? So x is number 1 through 5, and y is equal to 0 if you get tails and 1 if you get heads. Yes. Now I would like you to carry out the following calculations. First, well, I mean, here they are, right? Calculate expected value x and the expected value of y. Oh, Stephen, you're here. That's very good. I just saw your question, and I downloaded the file you submitted, and we can talk about it after class. Since you submitted your question in German, I'll answer it in German. All right, guys, are you ready for the expected value x and expected value y? Let's do that. So what's the expected value of x? Well, this is the summation of k multiplied by 1/5, right? Where just one k is 1, 2, 3, 4, on that, we're just averaging those things, and we say that it's the number 3, right? So the answer is 3 from the summation. What's the expected value of y? Well, there is a much more sophisticated way to calculate it, which will end up being still the same as I presented here. There is something known as conditional expectation, because you see, y depends on which coin you take. In this case, of course, the dependence is non-existent, since all the coins are fair. And the answer is 0 times 1/2 plus 1 times 1/2, or 1/2. Yes? Now to calculate variance of x and variance of y. Now for that, I need to calculate the expected value of x squared. And then I sum up k squared times 1/5, and I get this number. Yes, I get the number 11. And the same for what is variance of y. Variance of y is the expected value of y squared. Here it is. Yes, and minus the square of expected value y. So it's so it's 1/2 minus 1/4. You get 1/4 then. Yes, so variance of y is 1/4. Variance of x is the expected value of x squared, 11, minus the square of this number, so minus 9, which is 2. Good. Now, what is going to be, do you think, covariance of x and y? What's covariance of x and y? You can write the formula if it helps, guys. That's also at the beginning. When you're stuck, write a formula for it, right? What is this thing? Calculate it, write it out, and then think what it might be. See if you can answer it with calculation or without calculation. Yes, Gustavo, thank you. The answer is immediately 0. Now, why? What is x? X is the number on the coin picked, and y is outcome 1 or 0. Do you agree that since all the coins are fair, the outcome 1 or 0, y is not dependent on x, right? So that means that covariance will be 0. They are independent. And I actually took the trouble and carried the calculation. You see, what's covariance of x, y? Just for you to see how the calculation would look like if you actually torture yourself with it. Here it is. Covariance x with y, it's all the combinations of squares with x and y. So what can x be? X can be 1 and y can be 0. X can be 1 and y could be 1. Right? So how many total combinations can we have? X can be 1, 2, 3, or 5, and y is either 1 or 0. So there are total number of 10 summations to consider. Do you agree? Do you see that? For every score x, there is a score y times the probability those scores meet. So probability x equal to 2 and y equals to 0 is the probability that the scores meet. Yes? And when we can calculate what's the probability that they meet. I mean, I decided to do it. You can split it. You can see that they're independent, or you can just calculate them together. It's up to you, right? Because you can just, well, I mean, regardless, you would end up with this calculation, because you have, let's say, probability x equal to 1 times probability y equal to 1, given that x equal to 1. But it doesn't matter, right? It's just always 1/2 for y equal 1 or y equal to 0. It's always 1/2, and you carry this long and annoying calculation, and you get 0. Which, if you understood it in general setting, you'd know that you'd get 0, because here you have every x matched against every y, and the probability that x equal to the number k and y equal to the number j is simply probability x equal to k, probability y equal to j. Yes, they split. Make sense? Let me know, guys, if there's yes, when it's on the spot, it's a bit difficult to know if they're independent. In general, if the coins are not fair, they will not be independent, right? So for instance, if the coin is biased, maybe the probability that y will be equal to 1 is changed depending on the coin that you pick. But in here, they are all fair coins. Yes, so they are independent. It's very, guys, try to understand, think about it at home, and try to understand very deeply what is this covariance. It's, by the way, related to correlation, as some of you might know. Yes, so covariance is this, it's this measurement of how dependent the variables are. If covariance is close to 0, then it means that they are not very dependent, right? The closer to 0, the less dependent they are on each other. That's the idea that you can get from it. But regardless, here is the calculation, and you see it equals to 0, correct? And you don't want to do this calculation in general. You just have to understand why expected value of x times y equal to expected value x times expected value y. What is the condition and how it works? Okay, now what do I know about variance? Since the covariance is 0, I know that well, variance in general of x plus y is variance x plus variance y minus 2 covariance xy. And because covariance is 0, it's just the sum of the variances. Yeah. Now here is another example. 2 fair dice are rolled. Compute the expected value and variance of the sum on the dice. Question make sense? Oh, good. Let's look at it, guys, together. So let's recall what is the expected value of x and of y. They're each independent random variables. So we know that the expected value for each of them is 7/2. Do you see how we calculate it? It's just the summation 1 through 6, which equals to 6 times 7 divided by 2, and we multiply by probability, which is 1/6. Good. Now, what about the square expected value? The expected value of x squared, it's 91/6. So now variance for x and for y is the same number. It's 91/6 minus 7/2 squared, which is 35/12. Yes? We know that the expected value of the sum is always the sum of the expected values. The expected value of the sum is 7. Now, what about the variance? Because they are fair, covariance will be 0. Fair dies means that they are independent of one another, right? So the covariance is 0. And so variance of the sum is the sum of the variances. And we have 35/12 plus 35/12 is simply 35/6. Here is a harder question. Remember the matching problem, guys. Yes, the gentlemen and their hats again. Now, what do you think is going to happen here? So I want to calculate the variance for those gentlemen. In other words, if x is the number of times they pick their own hats, right? Number of gentlemen that pick their own hats. What's the expected value? We calculated it to be always 1. Remember that, right? And now we want to understand what is the variance. Can you calculate? I'll give you 6 minutes, and then we'll do it together. All right, guys, let's try it together. I'm sorry if it was too short of a time. So what do we do? First of all, it's nice to define indicator variables where, we have defined xk to be equal to 1 if the cave gentleman picked his own hat and 0 otherwise. And what do we know? We know the expected value of xk is the same as expected value of x1, which equals to 1 over n. Do you agree? Do you all see why expected value xk equals to 1 over n? If I focus on the kf person, then and I just look at the strings. We have a string of length n. Each number in the string is either 0 or 1, and I focus on the kf number. And I see that in my table, when I calculate this expected value, this kf number is 1 every 1 over n times, right? Because the gentleman number 3, for instance, is equally likely to pick any hat. Just focused on gentleman 3 without any information about others, this gentleman is equally likely to pick any of the n hats. You agree? So that expected value is 1 over n. Similarly, the expected value of xk squared, which is what? It's just 1 squared if the gentleman picks his hat and 0 squared otherwise, so it's still 1 over n. Do you agree? That doesn't change. That's just the probability of success. Now, what's variance of xk? It's the same as 1 over n, this number, minus the previous number squared. So it's 1 over n times 1 minus 1 over n, yes? And what do we know about the expected value of the sum? It's just the sum of the expected values, or n times one of them, which is simply 1. So the expected value is 1. And now let's calculate expected value of the product x1 and x2. Do you see that it is equal to 1 over n minus 1? Why is that the case? You can see that in many ways. One way is, this means what? This means it's equal to either 1 or 0. It's equal to 1 only if x1 is 1 and x2 is 1, right? So it's 1 times the probability it's 1, and 0 times probability it's not 1, but we don't really care. It's times 0. So we only care about gentleman 1 and gentleman 2 picking their own hats. So that would be n minus 2 factorial divided by n factorial. Do you agree? Because we have in the string, we have first number is fixed in the sequence. 1 is 1, 2 is 2, and then everything else can do what it likes. So and if you simplify it, it will be 1 over n minus 1. You can do it in other ways if you prefer, right? You can do it by conditional probability. So probability gentleman 1 picks his own hat is 1 over n. Probability gentleman 2 picks his own hat given gentleman 1 picked his own hat is 1 out of n minus 1. Yes, so you can do it in many ways. I hope you understand, guys, that this probability, so this expected value, it's also the same as probability for indicator random variables is equal to this number. Now, what about covariance of x1 and x2? That's the expected value x1, x2 minus the product of x1 and x2, which is what? Which is 1 over n and minus 1 over n squared, which is not 0, as you can see. We expected it not to be 0 because it's clearly not independent. Clearly, what happens with gentleman 1 affects what will happen with gentleman 2, because gentleman 1 could potentially pick hat number 2. So obviously it will affect, right? So it's not 0. Now, what is variance? We can calculate variance. It's what? It's the summation of the variances of the individual random variables and plus the summations of all combinations of xk with xj, where xk and xj are not the same. Now, how many such summations are there? So here, first sum can be reduced to n times variance of x1, since they are identically distributed variables. You agree? So x1, x2, x3, they have the same expected value, same variance. So it's n times the variance of x1, and this summation, how many terms do we have? We have 2 multiplied by n choose 2. Do you see that, guys? So that's how many combinations we have. Because it's either x1 combined with x2 from second parenthesis, x1 from first parenthesis, x2 from second, or vice versa, right? So how many combinations are there? For just pairs, n choose 2. And because you can order them from smaller to larger or from larger to smaller, it's multiplied by 2. That's the number. Are you following, guys? That's the more difficult part here. Do you see how I was able to reduce this scary looking summation to just 2 times n choose 2? Sure? So write yes, guys, if you see that. Thank you. And I hope it's not a coerced yes. I mean, you can obviously say no. And it's a very, I admire people that say no because, you know, others say yes. That's going with the crowd. Say no. Don't go with the crowd. Good. So what do you have? So we have this. N times variance of x1 is what? It's n and 1 over n, they cancel out. So it's 1 minus 1 over n. And what do we get here? It's just n minus 1 times this thing. And when I simplify it out, guys, what do I get? Very interestingly, I get 1. Do you see what it means, guys? So you expect that on average, you get only one person to pick his own hat, and variability on average, you will see sometimes 1, sometimes 2 people, sometimes 0 people pick their own hat, you see? So it's kind of hovering around 1. That's what you see on average. So variance is then trying to control or trying to describe how the numbers are jumping. So you expect the numbers to be jumping essentially from the center from 1 by plus minus 1. That's what this means. Yes? All right, moving on. So we are now up to this lecture. So we begin talking about binomial random variables. So what are binomial random variables? Okay, so a very, very standard situation, very important one. We have n independent trials, and each trial is success with probability p, failure with probability 1 minus p. Now, what's the probability that I get k successes? So x, when it's binomial, measures how many successes I get, right? So how many successes I get? It's a string of trials, first trial, second trial, right? So on k of them, I get a success. On n minus k, I get failure. Yes, so do you see where the n choose k comes from? So n choose k is, so how do I measure it? Which of the trials produce the success? So they are labeled trial 1 through trial n. K of them produce success. N choose k is the trials that produce success. The probability of having those particular trials produce success, it's p to the power of k times 1 minus p to the power of n minus k. And just to see a more concrete example, so suppose that we perform 4 trials and we got 2 successes. So this is trial 1 through trial 4. 2 successes means we have success. We could have success, success, failure, failure, or success, failure, success, failure, right? Or how many of them? You can see that 4 choose 2, 6 possibilities. You can say I listed all of them. That's what the n choose k is doing. It's which of them produce success, right? So it's the summation over all situations where you have k successes. So for each success pattern, its probability, look at it. I mean, I wrote it in differently, but it can always be rearranged. So the probability of success to the power of number of successes times the probability of failure to the power of number of failures. Do you see that? So in this case, I mean, I just wrote it, okay, 1/3 squared, 2/3 squared. But in here, it's 1/3 and 1/3, and in the middle, 2/3 squared, right? But you can always rearrange them to be success probability to the power of successes, that's to the power of k, failure probability to the power of failure. Yes, and then you add over all of them. Now, how many summations? You're adding the same number again and again. How many summations do you have? You have n choose k summations. Do you see that, guys? It's very important. I don't want it to, maybe I'm over-explaining, maybe I'm under-explaining, but it's a very important idea. I want you to not just remember the formula, but really see that it must work. Yes, please write yes if you understood this explanation. You understand where the n choose k is doing there and everything else. Very good. And still there are not 20 people, so I imagine others just lost consciousness.
Professor,
yes.
n choose 2, I understand, but I didn't understand 1/3 and 2/3.
Yes, very good. Thank you, Camille. And by the way, I was always wondering at your picture. I thought what you're playing.
Sorry, I forgot. Yeah. Oh, there.
Yes, you're so well camouflaged, right, in the background. So here is the idea. Okay, once again, what is this measuring? So this is called binomial distribution, and it's measuring within n trials how many successes we had. So we could have had 0 successes or 1 success or all the way to n successes, right? All of them could have been successes. Now, suppose I want to understand the typical, let's call the mass function. What's the mass of x equal to k? In other words, I had k successes. In this illustration, I have 4 trials and 2 successes. What's the probability of getting 2 successes? So it's the summation of those situations. It's the probability at 1 plus the probability of 2 plus 3 plus 4 plus 5 plus 6, right?
Yes.
What are those summations? Those are the different ways I could have had successes. I add up universes, right? So in this universe, first 2 were the successes, the next failures, and all the other ways of having 2 successes and failures. Now, how many ways can you have k successes, right? Exactly k successes. Well, n choose k ways. So because the probabilities for each, for 1, for 2, for 3, for 4, for all of them, the probability is the same. I'm adding the same number to itself. How many times am I adding the same number to itself? In general, n choose k times. In this case, 4 choose 2 times, you see? You see, because what 4 choose 2? 4 choose 2 means that's classifying based on the trial numbers that choose 2 trial numbers that produce the success. And choose k means choose is classified based on the k trials that produce success. Make sense?
Yes.
Right. Yes. Well, then of course you can see that the summation of all the probabilities, it has to add up to 1, right? So having between 0 to n successes, that's must have been what happened. And you can see that by just arithmetics, what is this? It's this summation. And you recognize this is the binomial theorem, yes? N choose k, p to the k1 minus p to the n minus k. It's the binomial theorem where x is p and y is 1 minus p. So that's the same as p plus 1 minus p to the power of n, and this cancels to 1 to the n. Yes?
Yes.
Good. Now, screws produced by a certain manufacturer are defective with probability of 1% independently of each other. The company sells screws in packages of 10 and offers money back guarantee if at most 1 of the 10 screws are defective. what proportion of packages sold must the company replace? Let's see if you can calculate. Make sense, the question, guys? So it means that you can return the set of 10 screws whenever there is one, whenever there is one or more. I think whenever there are two or more, but at most one screws, I think means two or more screws are defective, you can return it, right? This is definitely not the manufacturing company that produced me. I have many more screws that are defective, but yet nobody returned. So go and calculate. You don't have to finish the question, just write up the formula, right? So that you know what you would have calculated. All right, guys, here is the idea. So X is the number of defective screws, and the binomial distribution has parameters 10. In other words, we have 10 trials for each screw, and the probability of success of finding a defective screw is 0.01. Yes, and we want to calculate the probability that I have two or more defective screws, which is the same as 1 minus the probability of 1 or less. It's just easier to calculate 1 or less. So it's 1 minus probability x equal to 1 minus probability x equal to 0. The company must replace it if there are two or more, because they say at most one. I mean, right? I suppose just you have to be careful with the wording. At most one. That means that if it's one defective screw, they're not going to replace it. But if there are two or more, they will replace it. That's how we understand it. So the opposite, right? So yes. So what do we get? We get 1 minus this minus that, And those are the probabilities, you see. So it's 1 minus 10 choose 1, and this is the number, minus this is the probability of 0 defective screws. You agree? 0 means that first screw is not defective, it's 0.99. Second not defective times 0.99, and so on until the power of 10. And when you simplify it, maybe using a calculator, you get 4 out of 1,000 packages will have to be replaced. Yes. So for every 1,000 packages that they sell, the company has to replace 4. Here is another example. At each step, a randomly moving particle is equally likely to move 1 unit to the left or 1 unit to the right on a number line. If the particle executes a total of n moves, describe the probability mass function for the particle's new position, given that it starts at 0. So let's do it together. You understand what happens, guys? So the particle is beginning initially in position 0, then aimlessly moves left or right. And then from the next position, aimlessly moves left or right. And we want to understand where it ends up. So clearly, guys, what we want to know is how many left moves it made or how many right moves it made, correct? Because it will be number of right moves minus the number of left moves, and that's its final position, correct? So the success is left, let's say right move, success, left move, failure. Good. So let's say X is the number of right moves. Then the rest must be the number of left moves, and X then is a binomial random variable with parameters n. We have n trials, and probability is 1/2. Now, if X is equal to J, where is the particle going to be located? It means it moved J units to the right and n minus J units to the left. So the total position is J minus the units moved to the left, right? Units to the right minus units to the left. So its position is 2J minus n. Do you agree? You see what I mean by 2J minus n? That's just a description of the. It's a function of the variable x in essence. So y is equal to 2x minus n, and that represents the final position of the particle after n trials based on this analysis. Correct? Because we focus really on how many moves to the right we made. So the binomial random variable is the number of moves to the right, and y is not the binomial random variable, it's a function of it. Yes? So what's the probability that 2x minus n of that y is equal to k? That means 2x minus n is equal to k, which means if you simplify x, k plus n divided by 2 is x. And you can see that n plus k must be an even number, right? If n plus k is not even, then that cannot be, right? Divided by 2. So what is the situation? This means this is how many right moves executed, right? So from if y is position k, I can figure from there how many right moves were executed. That's the number of right moves. Yes, and that is n choose number of right moves, 1/2 to the power of right moves times 1/2 to the power of left moves, which because it's 1/2, it ends up being just 1/2 to the power of n. Yes, and in particular, what can y be equal to? Clearly, y can be equal to minus n. That's when all the moves are to the left, or it can be equal to minus n plus 2. You see, all you do is just replace x equals 0, replace x equal 1, replace x equal to 2, and you get all the possibilities for final position y. And in general, y equal to minus n plus 2j means that the probability is n choose j 1/2 to the n. Yes, makes sense, guys? When you do that, when you review, try to think of it and solve it yourself. Here is a maybe slightly more interesting question. I remember I was wondering about such things. You know, I was once in a country club a while ago, and there were many guests. And it always was surprising to me that you could order a dish, you know, it's already prepaid, you know, when you're in the country club. So you have those lunchtime or dinner times, and then you can very frequently order the same dish again, or they seem to always have a dish available for you, right? How do you do such things? So, and I also worked in catering at some point. That was, I still have nightmares. It's like I have this thing, little girl, please don't eat this food. It's just because I've seen how it was made. So here is the situation. So suppose in the country club, we have a certain popular dish, and each guest independently orders that dish with probability 0.8. Today, there are 100 guests, right? So what is the probability that all of them will order this dish, guys? Understand? So the dish is, so they order this dish or something else. So this dish is so popular, it's 80% likely to be ordered. What is the probability that all the 100 guests order that dish? Very good, Chiara, and that is not a very large number, right? So what is that probability? 0.8 to the power of 100 is 2 times 10 to the minus 10. It's very tiny, you agree? It's a very, very tiny number. So clearly it does not seem worth to make the dish to make 100 favorable dishes. Imagine you have to be prepared before they come, right? It's a waste of resources to have this dish available for every single person, correct? Now, here is the question. So how many dishes should the country club prepare if management wants the probability of running out of stock to be less or equal to 1 out of 1,000? You understand? So they want, so they might say to some guests sometimes, what in 1 in 1,000 guests, sometimes we say, oh, I'm so sorry, the dish is no longer available. Yes. So how many dishes must they have ready so that the probability of running out does not exceed 1 out of 1,000? Well, guys, let's do it together, I suppose, right? So this, of course, can be, and this is already an annoying question to solve using binomial distribution, but imagine that the number is m, where m is less than 100, right? So what's the probability that more than m is required? So in other words, I made m dishes, yes? And m is not 100, and I have 100 guests. What's the probability that more requests than m follow? Okay, that's probability the requests are from m plus 1 to 100, and that's 10 choose the number of requests, the probability of that request, probability of that the others don't have that request. It's this number, and we want it to be less than or equal to 1,000. Yes. You can just make you can actually do something much better. We will study approximations to binomial theorem. It's a normal distribution and whatnot, and that was coming later. But you can also, I suppose, just kind of take the summation and play with the number m, you know, make a computer program if you want, right? And you can see that that what happens is that you want m to be so that this probability happens when m is bigger than or equal to 91. So that means that you should make 91 of those dishes. Okay, so in other words, this number is for the first time less than 1000 when m is 91. That means when you have, what is it, when you have 91, that's how many you make, right? So yeah, so you need to make 91 dishes. Good. Okay, here is another question, also maybe interesting. So you have an electronic device, has an odd number of identical components. So maybe imagine an airplane, right? So it has odd many propellers, maybe a propeller on the nose, or maybe a propeller on the nose and two propellers on the wings, or maybe two propellers on the wings and one on the nose. You understand, it has odd many functional components. And each component is likely to fail with some probability p. The components function independently of one another, supposedly, right? I'm not sure if it's true of propellers or airplanes or anything, but the question is, what are the conditions on p if the device with 2n+1 components is more reliable than the device with 2n-1 components? Okay, so in other words, which airplane is safer, one with 3 propellers or one with 5 propellers? Given p, of course, right? How reliable is the engine? So if p is large or small, I mean, what do you think? Okay, so in other words, it's a function of p. What should you do? If p is a particular number or by a border of a particular number, should you make more of those devices or less? Okay, and the machine fails if most of the components fail. Good. So that's when you have a more complex system or a less complex system, which one is better? It's a little bit of a hard question. I'm not sure you want to think of it or you want to solve it together. It's hard to solve it, I think, in such short amount of time. Yeah, let's do it together. You agree, guys, right? So, and don't worry, I am not depriving you of extremely difficult questions. You know, you will have them on the exam and enough time to think of those. Okay, so let's look at the solution. So x is a binomial random variable with 2n+1 trials and probability of success in this case failure, right? So it's probability p. And y is another binomial random variable with fewer trials, with 2n-1 trials, right? Then we have the device that has more components, that is device x, is more reliable or less reliable. Let me think that which is one. Reliable, then what do you have? You have the probability that x is less than or equal to n. That's the more than half mark, right? Is bigger than or equal than the probability y less than or equal to n-1. You see what I mean? This means that the device is still working, right? Because look at it, 2n+1, at most n components can break for the device to still be working, right? So on the left, you have probability device x is working. On the right, you have the probability device y is working. And device x is with more components is more reliable if this probability is higher than this probability. Do you agree? Right? Because here it's more than half of its components are working, and the probability of that is more than in this y, that more than half of its components are working. Is it clear? So then we can try to compare those probabilities. So what we have is, we're going to say N0, N1, and N2 be the events of 0, 1, and 2 failures in the first two components of device X. Basically, I'm trying to make X comparable to Y, because you see, X is having two extra components compared to Y. Do you agree? So what do we get here? Then probability that X is less than or equal to N. Probability that X is less than or equal to N is that same probability given N0, given N1, and given N2, right? So that means that that we have 0 failures in the first two, 1 failure in the first two, and 2 failures in the first two. You know, imagine the propellers are labeled 1, 2, 3, and onwards, right? So what do we get here? So the probability of no failures is what? So what is this? This is probability of no failures in the first two components is 1 minus p squared, right? And the probability that X is less than N, given that there were no failures, is just the probability that Y is less than N, right? Y less than N, because how should I say that? Yeah, because here we have no failures. The remaining, now what is this? Once we know this information, right? We now the remaining ones. Just the remaining thing is just the Y parameter. It has 1 second, let me think. So Y then refers, of course, to the distribution that we have left, correct? So we removed 2 units, so now we have 2n minus 1 units available, right? And then Y is just a variable that tells you how many of those are working, right? Now, we should have less than n failures, correct? You with me, guys? It's a little difficult, so we should have less than n failures for the variable X. What does Y represent? Y simply represents, forget about left and right, Y definitely represents the distribution on 2n minus 1 trials. We already know what happened to 2 trials, right? 2 trials were not successful, so I should not have n successes in the next remaining trials. Do you agree? Because if I have n successes in the next remaining trials, more than half of the components fail, right? So you understand, this means that we have less than n failures. So this means we have less than n failures in the remaining 2n minus 1 components, right? Or what happens here? Suppose in the second part, one component failed. In other words, exactly one failed, right? Among the 2 initial components. So what's the probability of exactly one failing? Well, it's 2 times probability of failure, probability of not failure. So one of the 2 failed and the other did not, and it could be either first failed, second did not, or vice versa. That's why you have 2 times that, yes? And if we already had 1 failure, we cannot afford a total of n failures. Right? In other words, we cannot afford a total of more than n failures. So we can at most afford in the remaining trials n minus 1 failures at the very most, you see? So we can afford here n failures. Here we can afford n minus 1 failures. And for the last situation, we can afford only n minus 2 failures because we have 2 failures. Yes. So what happens there? Look at it. So then I can simplify it. Let's see, we have this thing. I just simplify it. And then I can now yes. Okay, yes, I split it where y is equal to n, sure. So I look at this part, y less than or equal to n. That is the same as probability of y less than or equal to n minus 1 plus the probability of y equal to n, right? This part I split into those two parts. You can see this. Then what do I do next? Then this one I don't bother. You can see it's here. And then this one I split into y less than or equal to n minus 1 minus y equal to n minus 1, you see, because it's y less than or equal to n minus 2, so it's y less than or equal to n minus 1 minus the probability y equals to n minus 1, right? Times p squared. And then I just recombine. The reason I do the y less than or equal to n minus 1 is because I'm searching for this part. You see, I'm comparing this part to that part. Good. So what do we have here? So then I just factor it out. I have probability of y less than or equal to n minus 1 times all this probability here, plus probability of y equal to n times the probability here, and minus the probability y equals to n minus 1 times this probability here. And so when I simplify it, this is a perfect square. This is equal to 1. So it's the probability of y less than or equal to n minus 1. And what is this? This is this part, y equals to n, is just 2n minus 1 choose n. And that's the probability of choosing that, and multiplied by 1 minus p to the squared. It gets you to this number. Yeah, so this number becomes this number. And then minus what you have here. It's 2n minus 1 choose n minus 1, and then the probability. That's what you simplify. And what do you get? You get probability of y n minus 1 plus everything here. You can see, right? Everything here. And we suppose that this is the probability for x less than n. I compared it to y. You see, it's the probability that x is less than n. And we want this number. So it's probability of y less than or equal to n minus 1 plus this number. And I want it to be bigger than or equal to the probability that y is less than n minus 1. So this has to be positive. You agree? This number in here in this parenthesis has to be positive. That's how I'm thinking. And then it's this number here. It's positive. And when I simplify it, guys, what do I get? I get that p has to be less than or equal to 1/2. In other words, well, you might have suspected that 1/2 is something to do with it, right? In other words, what is this saying? So a system that's built out of unreliable, a system that's built of, so p is a failure, right? P is failure. So whenever p is smaller than 1/2, the parts are more reliable. So if you have parts more reliable than basically the probability of failure is less than 1/2, then you want to have as many parts as possible. If the probability of failure is more than 1/2, then you want to have fewer parts. You see, 1/2 is bigger than P, means then if failure is smaller than 1/2, you prefer more parts. Because what is this? This is the probability of more parts. Yes? Sorry if it was difficult. It was difficult, but I enjoyed solving this question a while ago. And today I remembered now what I did a time ago. Good. Yes. Any questions, guys? Probably we only have 1 minute. There is no reason to go into the next topic. We don't have time for that. So if you don't have anything, I suppose goodbye. Enjoy your weekend. And I will try to grade your exam. I'll probably try to force myself to do a question a day or maybe 2 questions a day. It will be difficult. I don't enjoy grading. So be patient, guys. I promise that by the end of the semester, you will have all your grades.